Hi, welcome to lesson 18D, Integration. So over the past couple of days we've looked at areas under the curve, which is basically the fundamental theorem of calculus, the first principles form or method of finding the antiderivative or the integral of a function. And so now we're just going to get more into the integration part. We're going to use more of our skills as opposed to going through areas under curves anymore. We'll just go right through the actual intuitive part of integrating. So we've seen in past days that if we wanted to find the antiderivative of, say, x squared, that antiderivative would actually end up being 1/3 x cubed. Because if you take the derivative of this, in the derivative you take the exponent down in front, you multiply it by the coefficient of that, and you reduce the exponent by 1. So 3 times 1/3 will just give you 1, and when you subtract 1 from 3 you get 2. Okay, so that indeed would be the antiderivative of this function x squared. Likewise, if we had x to the power 5, for example, the antiderivative of x to the power 5 would be 1/6 x to the power 6. Okay, so to check this, we take the derivative of this, bring the 6 down in front, multiply it by a 1/6, we get the 1 in front, the coefficient, and then we subtract 1 from this exponent to get 5. Okay, so that's basically how things have been working. Now, we know that the derivative represents the gradient of the tangent at any point. So suppose we had, and I'll just do a quick sketch here, just some general function. If we've got a grid here, we've got some sort of function. I'll keep it simple and just say it's some sort of even-powered function. If we had the gradient at this point here, we know that the gradient represents, or the derivative represents the gradient of the tangent at that point. So the antiderivative of x to the power 5 is 1/6 x to the power 6. So if we take the derivative of this, if this happened to be this function here, and we take the derivative of it, we get x to the power 5. And so that gives us the gradient of the tangent at that point. Now what if this wasn't just 1/6 x to the power 6? So as you can see, there has been some vertical translation away from the x-axis. So suppose that's +3, for example. That vertical translation has no effect on the gradient. So when you take the derivative of this, we see that this 3, being a constant, will just become 0, and so the derivative of this becomes x to the power 5. So that vertical translation has no impact on the actual gradient of this tangent at that point. If this function were drawn down here, for example, the best I can, that gradient is going to be the same even if it were translated down here. Okay, so that gradient is the same. The gradient of the function is going to be the same no matter where the function is translated. So therefore, when we take the antiderivative or the integral of a function, we need to add in the possibility of having some kind of constant there, some sort of translation. So if we had x cubed, then the antiderivative of that would be 1/4 x to the power 4 plus some constant c. Because when you take the derivative of this, we just get this. That constant disappears when you take the derivative of it. So we need to add in this constant of integration, they call it, to account for any sort of constant that might have been included in the original function. Okay. So in the textbook we see this capital F of x, this capital F prime of x, when you take the derivative of that capital F of x, we get f of x, like the derivative, which is basically the original function then. Then the integral of this is going to give us uppercase, or capital F of x, plus c. Okay, that constant of integration. Okay, this uppercase f of x is the antiderivative of this function f of x. So when you take the derivative of the antiderivative, we actually end up getting that original function that we were looking at. Okay, we call this the indefinite integration because there are no indices here to tell us over what range we're taking the integral. Okay, that's the indefinite integral. Now, when we looked at limits in the past, say the limit of 3x squared as x approaches some value, let's say it's 4, that when we take the limit, we can actually take this 3 and put it in front, because that 3 has no actually impact on the actual taking of limits, like the actual limit calculating process. So that 3 can go out in front, and then we're taking the limit of x squared as x approaches 4. And then when we do that, then we just multiply by the 3 later. Okay, and same thing for derivatives. If we're taking the derivative with respect to x of, say, 4x to the power 5, we can move that constant out in front and then take the derivative with respect to x of x to the power 5. Okay, so in this case, when you take the derivative, of course, we bring the 5 down in front, multiply it by the 4, and then reduce the exponent by 1, so it gives us 20x to the power 4. And in this case, we get 4 multiplied by 5x to the power 4, which then simplifies to 20x to the power 4 anyways. So in the cases with limits and taking derivatives, if we have a constant in front, we can just move it in front of that limit or the derivative notation, and it ends up being the same thing anyways. So the reason why I bring that up is because when we take the integral, suppose we take the indefinite integral of 3x to the power 4 with respect to x, we can see that it's going to be the same as 3 multiplied by the integral of x to the power 4 with respect to x. Okay, so if we take the integral of this, we get 3 over 5 x to the power 5 plus c. And if we take the integral of this, we get 3 multiplied by 1 over 5 x to the power 5 plus c. And then when we multiply this in, we get 3 over 5 x to the power 5. Now, we could say 3c, but we don't need to say 3c. We can just keep that as c, because it's still just a constant, and when you take the derivative of this, that constant is just going to disappear anyways. So as it's not wrong to write 3c in there, in this case, we don't need it. So generally you will just write a c anyways, okay, because it's just going to be a general constant. Okay, so that's basically it. Just a couple extra little notation notes. So the integral of k f of x dx, that's going to be equal to k multiplied by the integral of f of x dx, where k is a constant, of course. And then if we were to take the integral of a sum of functions, suppose we were, or a difference, doesn't really matter, sum or a difference of f of x g plus or minus g of x with respect to x, that's just going to be the integral of f of x with respect to x plus or minus, depending on what we have here, the integral of g of x dx. So it's just the same as taking derivatives or limits, where you just take the limit or derivative in parts in terms of each individual term. Just do it one at a time. Okay, so that's the basic nuts and bolts of this part of the lesson in 18D. We're going to look at a couple examples tomorrow in class. What I'd like you to do is take a look at the examples in the textbook and click on the self-tutor to have her explain the solution for you. And then take a brief look at these examples, these questions, these exercises from 18D and 18E. We're going to go over some of the rules of integration on 18E in class, and then we'll look at some examples in class as well. So just peruse these, actually not even peruse, just kind of take a quick look at them, just see what kind of things we're going to be tackling tomorrow. And then once we go through the examples, then you'll have an idea, a better idea of how to handle all these antiderivatives and integrals. So thanks for watching, and we'll see you in class.